the tan function y equals tan x. Okay. Now, before we do this, I want to just review a little bit about what we've already seen around tangent, the tangent ratio, and the unit circle. Okay, so if we're on a point on the unit circle, okay, the radius is 1. The height of that point is the y-coordinate, and the horizontal distance is the x-coordinate. Okay, so the tangent of this angle theta is equal to y over x. Okay, now if one of the points is 0, 0, this is the point 0, 0, and this is the point xy, that ratio of y to x, because we're starting at the origin, actually represents the slope of that terminal arm, right? y2 minus y1 over x2 minus x1. Well, the x1, y1 is 0, 0, so it's just going to be y over x. So we can think of the tangent in terms of the slope of the terminal arm. Okay, this is the slope of the terminal arm. Okay, so that's one way to think about the tangent ratio. But we can also think of it in relation to sine and cosine, because this point xy on the unit circle is cosine theta, sine theta. Okay, so tan theta also equals to is also equal to y over x sine theta over cosine theta. Okay, and when I'm graphing the tan function, I find it helpful to think about it in terms of the sine and cosine function, because I have a really clear picture in my mind as to what sine theta looks like and what cosine theta looks like. So, for example, because tangent is written in terms of sine and cosine, I'm going to have a problem when cosine theta equals 0, right? So tan theta is undefined when the cosine of theta equals 0. Now think about the cosine function. Okay, so without any transformations, here's 2 pi, pi by 2, 3 pi by 2, 1, negative 1. Okay, there's the basic cosine function. And then that repeats over and over and over again. So if that's the cosine function, where am I going to have some problems on my tangent function? When cosine equals 0. So where does that happen? Yeah, pi over 2, 3 pi over 2. The next one would be 5 pi over 2. So it starts at pi over 2, and then you add multiples of pi, right? So cosine theta equals 0 for theta equals pi over 2 plus or minus multiples of pi. Okay, so when I'm thinking about my y equals tan theta, okay, here's 0, pi, 2 pi, negative pi. Okay, so the problem starts at pi over 2. So here's pi over 2. And then I add multiples of pi. So pi over 2 plus pi is 3 pi over 2. Here's 5 pi over 2, right? I'm going to have some asymptotes there. This would be negative pi over 2. Yeah, so whenever cosine theta equals 0, I'm dividing by 0. I'm going to get a vertical asymptote on my tangent graph. It's a lot of vertical asymptotes. Well, the nice thing, though, about y equals tan theta, it is a lot of vertical asymptotes, but just like sine and cosine, tangent, y equals tan theta is periodic. Okay, so we're going to see essentially one picture that just repeats over and over and over and over again. Okay, so that's one thing I need to consider, is that tan is undefined whenever cosine is equal to 0. And that starts at pi over 2, and then we keep adding multiples of pi. Okay? The other thing is that the numerator of tan theta is sine theta. So tan theta is going to equal 0 whenever sine theta equals 0. So if I think about y equals sine theta, that'll give me some more points on my graph. Oh, I'll do this. Okay. Here's 0, here's 2 pi. Just notice how I'm setting this up, by the way. I start at the beginning of the period, end at the end of the period, then I do the middle, and then quarters. Okay, that's how I do my scale every single time. And then I'm going from 1 to -1, so 0, 1, 0, -1, 0. Okay, so there we go. Okay, so sine theta is the numerator of tan theta. So if the numerator is 0, the whole thing's going to be 0. So some other points that I can get on my tan function is looking for when sine theta equals 0. Because when sine theta equals 0, tan is sine over cosine. 0 over anything is 0. So tan theta will also equal 0. Okay, and this happens starting at 0, and then we add multiples of pi. Okay, so in terms of my tan function, what does that tell me? All of these points are going to be 0. Oh, sorry, I scrolled up too fast. Okay. And then there's a couple of other key points that I want us to think about, which is, for what angle is the tangent ratio equal to 1, where the ratio of the opposite to hypotenuse is equal to 1? What's that angle? If the opposite to hypotenuse is 1, what do we know about the opposite? Or sorry, not opposite, adjacent. Oh, sorry. The tangent is opposite over adjacent. So if opposite over adjacent equals 1, what do we know about the opposite and adjacent? Yeah, 40. They're equal to one another, right? That happens in isosceles right triangle. So that's another thing that I want to think about. So first thing, I'm going to put in all these zeros. There we go. And then the other thing that I want to think about, and we're going to get to this in a second, let's put in 1 and -1. Okay, so let's look at the unit circle. Yeah, so the tangent ratio is equal to 1. When this is 45 degrees. If it's 45 degrees, these are equal. Anything divided by itself is 1. So tan theta equals 1 over here when this is, now the whole thing from here to here is pi by 2, so this would be pi by 4. Okay, so that's our angle in quadrant 1, also our reference angle. Where else is tan positive? Quadrant 3, yeah, so this guy is another angle where tan theta equals 1. Now starting over here, that's 4/4 plus 1/4, 5 pi by 4. Shh. Okay, so that's when tan theta equals 1. So it's pi by 4. Well, that's going to happen right in between 0 and pi by 2. Okay, it also happens at 5/4. That happens here between pi and 6 pi by 4 would be 5 pi by 4, so here. Okay, where is tan theta equal to -1? Let's think about that too. I'm going to do that over here. Yeah, in quadrant 2 and 4. Right, so here, that's 3 pi by 4. And here is 7 pi by 4. Or if you want, you can also think of this as negative pi by 4. Okay, so let's stick in those points. So at 3 pi by 4, tan theta is equal to -1. Okay, well that's going to happen between a half and a whole. It's going to equal -1 over here. Okay, it also happens at 7 pi by 4. That happens right here. Negative pi by 4 happens here. Okay, so what we're seeing in terms of a few of these points is these 3 points seem to repeat themselves. Okay, now if we connect these and use the asymptote to sort of guide us, that would be one period of the tangent function. Okay, and then it's going to repeat. There's another one. This is also, it'll equal 1 over there. There's another one. Okay, so this is what y equals tan x looks like. Okay. Now, in this course, we don't tend to do stuff like, you know, horizontal shifts and vertical shifts, but it's possible that we could change the period, right? That would work the same way as the other ones that we've seen do. But the period of this function is not 2 pi, it's pi. Okay? So now let's actually talk about some of this stuff. Now we already sort of talked about this already, right? So we'll just repeat this quickly, but on the unit circle, do you guys have questions?
It's just we thought that we were supposed to be doing.
Oh, you were doing that already? Yeah. Okay, well then I don't need to write it down, do I? We're good? Do I need to go through this anymore? Huh. I'm just putting the same thing in, right? Right? So this is 1. Here's my theta, right? So tan theta equals y over x, which is sine over cosine. Okay, and it's also, this is the slope of the terminal arm. Okay, that's really all that I wanted to put in here. Now, what you'll see in your notes is that you get this picture right here. Okay, now the reason, some of you are like, why did we have to do that?
You're trying to explain how.
Well, yeah, like, you know, it's, I know what's going to happen when some of you go on and then we actually have to do stuff with this and you have to understand why, and then you're drowning, right? So if you think about it in terms of the stuff that we already know, you don't have to come up with that yourself, but if you can follow, that's a good state to be in, right? Okay, but we see the same sort of thing, right? So there's these vertical asymptotes starting at pi by 2, and then we add multiples of pi, right? When is it 0? At 0, and then we add multiples of pi. Okay, so the vertical asymptotes, let's just write some of this information down. So first thing is the curve is still periodic. It's not continuous, but it is periodic. There's a period that keeps repeating over and over again. The vertical asymptotes occur at when x or theta, what are we using here? X, theta. I'll use theta. Yeah, when theta equals pi over 2 plus or minus pi n, where n is an element of the natural numbers. Okay? And just a reminder, this is when cosine theta equals 0. Okay, so those vertical asymptotes come from the fact that the denominator of this function is cosine theta. So whenever that's equal to 0, we're going to have a problem. Okay? Tan theta equals 0 when theta equals 0 plus or minus pi n. N is an element of the reals. And this comes from when sine theta equals 0. Okay? So where does it equal 1? It equals 1 at pi by 4. Right? Quarter pi is in between 0 pi and a half pi. Okay? And that's because we're looking at pi by 4 is an isosceles right triangle. So the opposite and the adjacent will be equal to one another. So their ratio will be 1. So this is at theta equals pi by 4 plus or minus pi n. Right? And yeah, we still keep adding. This period over here is still pi, right? So I don't have to write any more out other than that one. Tan theta equals -1. Now, you could put 7 pi by 4 if you want. 7 pi by 4 is this point actually over here. But I personally prefer to think of it as negative pi by 4 over here because I imagine the unit circle and just going 45 degrees in the opposite direction. And I like thinking of my tan graph sort of having rotational symmetry around the origin. That's kind of a helpful image for me. So this happens when theta equals negative pi by 4 plus or minus pi n. N is an element of the naturals, right? But I think the point that I'm trying to make is that this angle over here, you could add pi to it and make it 3 pi by 4. That's fine, right? Okay, you just have to be hitting one of these points where it's actually equal to -1. Okay, so there is no max or min. Okay, the range is everything. There's an arrow going up, there's an arrow going down. So the range is y is an element of the real numbers. The domain is limited by these asymptotes. So the domain is that x cannot equal pi by 2 plus or minus pi n, where n is an element of the real, not the reals, the natural numbers. Okay, but beyond that, x is any real number. Okay, so besides for those restrictions, x can be anything. Okay, the x-intercepts occur whenever, here, the x-intercepts are here, 0 plus or minus pi n. Oh, sorry, I'm using like theta and x. Let's be consistent. I think I used theta before. I'm just going to use theta. Okay, so x-intercepts, theta-intercepts are when theta equals 0 plus or minus pi n. N is an element of the natural numbers. And the y-intercept, really only one y-intercept, and that's at 0. Okay. We're almost there. Okay, so now we're going to do the same thing in degrees. This is just an exercise, though, because we don't really ever graph things in degrees. But I suppose, like, the key points that you want to think about is 0 radians, pi radians, 2 pi radians, and then pi by 2, 3 pi by 2, right? You need to know what's sort of happening at those points. And then it's helpful to kind of know where tan is equal to 1 and -1 as well. So one thing that I like to do with the tan function is put my asymptotes in first. Okay, so I know that my asymptotes are at x equals pi by 2 plus or minus pi n. Okay. Now in degrees, pi by 2 is 90 degrees. Plus or minus 180 degree n. N is an element of the natural. So I'm going to start here at 90, and then the next one will happen at 270. Okay, so there's my vertical asymptotes. I also want to know where it's equal to 0, and that happens at 0 and then multiples of pi. Multiples of pi are same as multiples of 180. So there's a point, there's a point, there's a point. Okay, and then that 45 degree angle, the pi by 4, that's where it's equal to 1. So 1 is over there. And then you can kind of get the rest of it through rotational symmetry. Like this guy's going to be -1 down here. Okay, so here's the 0 in between 180 and 270, right there. It's going to equal 1. And in between 90 and 180 right there, it'll be -1. This is a very large scale, so it looks very spread out. Okay? Here we only have a little bit of it, but there we go. Okay? So in this sort of little exercise, all we're really doing is translating the radians into degrees. Right? And with the tangent ratio, the key sort of angles that I'm concerned with are 0, 90, 180, 270, 360, but then all of those 45s as well, where the reference angle is 45, because that's when tan is equal 1 or -1. So I'm also curious about this, 45 degrees, and then this would be 135 degrees. This would be 225. Why can't I add today? 225, right? And this is at 350. So I'm curious about those points too, because then I can plot the 1 or the -1. Okay? All right. Last question of the day. Okay. A small plane is flying at a constant altitude of 5,000 meters directly towards an observer. Okay, so constant altitude means the height doesn't change, flying towards an observer. Draw a diagram that represents the relationship between the horizontal distance in meters from the observer to the plane and the angle in degrees formed by the vertical and the line of sight of the plane. Okay, so let's start with that diagram. Okay, so I need an observer. And I believe we're told the ground is flat. Yes, ground is flat. So I'll put the ground in there. It's always good for someone to be standing on the ground. And then I have a plane. So here's my plane. Oh, you're right. Okay, yeah, you're right. There is a domain. Okay, so erase this. Yeah, you're right. That's all you'll see. I think the reason why I know you guys are getting frustrated with me, why I'm making so many mistakes is that we don't ever do that kind of thing. Like graph y equals tan x in degrees with a restricted domain. It doesn't happen in reality. But you're right, I need to pay attention to details. That's not an excuse. Thank you for calling me out. Okay. back to the plane. So the plane has an altitude of 5,000 meters. And it's flying towards this observer, but the altitude doesn't change. So horizontally, it's flying towards the observer, but vertically, it's not changing its height, right? So right now, what we want to know is the relationship between this distance x and then the angle in degrees formed by the vertical, there's the vertical, line of sight. The line of sight is there. So we're curious about this angle. The relationship between that angle and that horizontal distance. Now when the plane moves closer, I'll do this closer image in a different color. Okay, the height is not going to change. So if the plane's over here, okay, what's changing is this and this. Okay? But the height doesn't change. So it's the plane is sort of cruising along like that. And we're paying attention to the angle between the line of sight and the vertical and that horizontal distance. Okay, so far so good? Okay, so this is still 5,000. Now, if I try and come up with a relationship between that horizontal distance and the angle, I can use tangent because this is a right angle. Tan theta is x over 5,000. Okay. Now, this is a little bit confusing because we're not used to using the x variable in this way, but ultimately, this is a tangent function, okay? And so what we sort of want to isolate in terms of being the quote-unquote y variable, the dependent variable, is in fact this horizontal distance. It may be easier for you guys to use a different, or for me, to use a different variable there. Let's maybe change this instead of to x. Let's make it d. Because when we see the variable x, what we think of doing in terms of functions is isolating that x. Okay, but in fact, we're going to write this relationship as a tangent function because there's no sort of clean way of isolating theta. We would have to use tan inverse to isolate theta. That would not be very pretty, right? So if we want to graph the relationship, we would want to isolate the d. So I'm going to multiply both sides by 5,000, and what I will see is d equals 5,000 tan theta. Okay. So this is a tangent function that has been stretched vertically by a factor of 5,000. Now, when you have these vertical stretches with the tangent function, all you really need to worry about are those points 1 and -1. 1's going to move to 5,000, -1's going to move to -5,000. Okay, so that's really all that I care about. Horizontally, nothing's changing. So I'm going to start to graph this. And I'm going to change this to theta and this to d, because otherwise I get confused. Now, the scale right now is not conducive to graphing this, because those points 1 and -1 vertically are going to move to 5,000 and -5,000. So I'm going to change this. Let's make it here, 5,000. 3 little squares is 5,000. This is -5,000. Okay? Now, the zeros happen at multiples of start at 0, then add 180. So that's 0. 4 squares is 90, so another 4 will be 180. Okay. And then, but realistically, there would be a restricted domain here because we're actually looking at something physical where that theta angle is part of a triangle. The asymptotes are going to happen here. And then the only other one that I see is at the -90 degrees. And then in between 0 and 90, which is the 45 degrees, okay, that's usually where I have the point 45 degrees 1, or pi by 4 1, because the tangent of 45 degrees is 1. But now it's going to be 5,000 times 1. So this is now over here. And this is down here in between. Okay, so here's a picture of that function. Okay, now use characteristics of the tangent function to describe what happens to the graph as the plane flies right from the right of the observer to right. I think I meant to say right over. Use characteristics of the tangent function to describe what happens to the graph as the plane flies from the right of the observer to the left of the observer, maybe? I don't know. I think what I wanted to talk about is what happens when that plane is right over the observer. So let's say when it's on the right side, okay, that distance would be considered positive. The horizontal distance is positive. Okay, and the tan of that angle is also positive. Okay, is positive. Okay, what about when it's right over the observer? So here's the observer, here's the plane. What's the horizontal distance there? 0. And the tangent? 0, yeah. So that's this point here, 0, 0. This is when the plane is right over the observer.
It's tan negative. Tan theta negative.
Say that again?
Right there. You have positive tan theta.
Yeah. No, it's positive. Sorry.
Positive. Wait, what?
Yeah. We're looking at here, right?
Wait. Okay.
And then when it's on the left, right? So that's this picture here when it's right over. If it's on the left side, then the horizontal distance will now be negative because we have to use the observer as sort of like an origin, right? If we want to quantify horizontally how far the plane is on one side of the observer to the other, you know, think of it like a vector. If we wanted to just use a single number to describe that, rather than using directions with words, right or left or whatnot, you would have to add a negative value to that. So now the horizontal distance is negative. Okay? And if the horizontal distance is negative, then the tangent will also be negative. Because the tan of the angle comes from the horizontal distance and the vertical. Now, the vertical distance is not going to be negative. It's always 5,000. And in fact, that would not be a good situation if the vertical distance, rather, of the plane was negative. Okay? So tan theta, because this denominator is always positive, will have the same sign as the distance. Okay? All right. Questions?